Hopefully that works. Okay, so welcome everybody. Tonight we're going to continue our discussion on diffusion policy. I think we'll start with a quick review of last week, and then we kind of finished most of the paper, I think. We'll jump into some of the data and the code. And then if we have time, look at this paper scaling up and distilling down. I think that this was the summary. Can you guys read that? That's a little fuzzy on my end, but
it is fuzzy on our end also. I don't know if you use the optimize for. Okay.
So yeah, I think it's probably when I grabbed the image actually. Why don't we'll go ahead and just use it anyhow. I don't know if I've got the other. It's essentially this part right here. That might be a little more clear.
On my end, even this is very fuzzy. I don't know how others are seeing it.
Yeah, it's very pixelated. I don't know if you have low bandwidth.
Oh, I hope not. Could be. That in that case, I don't know if I can fix that if it's a bandwidth issue. It's very clear on my end, so I guess this is the best that I can do. Let me know if it's
slowly getting better as it sits.
Okay, that's going to be a problem then. Okay, so anyhow, just quick review then. This paper is about using a diffusion process, conditioned diffusion process to do robot control. The idea is they take in image and the robot position information, robot pose information. They take observations, some number of observations. In practice, they're using 2. They run it through a diffusion-like process that predicts a series or a sequence of actions that are required to achieve a goal. And then they kind of run for a certain horizon. They'll run on those actions more or less open loop, come back and get another set of observations, run the diffusion process again, et cetera, until they reach their goal. They do condition the diffusion process in 2 different ways. So the epsilon theta of the observation and the action vector, and K is the iteration step, the diffusion iteration. So they condition this using 2 different methods. One is CNN based, where they take the observation, run it through this film feature-wise linear modulation. So they take the output of the CNN. They do this linear modulation of the features and do that a few times in the CNN stack. In practice, they're using a UNet, so those are the multiple steps in or multiple CNN layers in the UNet. They iterate on that K times, and that's the diffusion, conditioned diffusion. The other style that they use is a transformer-based, where they instead embed the action, embed the observation, and then use kind of a masked attention, again iterating K times to get the diffusion. That's the general process. The results, these pictures down here depict how the diffusion process. So the color of the pixel is how far into the future, like the purple ones would be recent, and then the yellow ones are the further out in time predictions. So the idea is, I think this is kind of visualizing how the diffusion works. You start with some distribution of actions. In this case, by the way, actions, they use position control. So the actions are, where do I want my end effector to be in this particular task. This task is to take the T and move it to where the little T outline is. So that you can see that diffusion takes this distribution of possible positions and gradually refines them down until you get a trajectory that will achieve the goal. Okay, so that's the quick summary. Any comments or questions from anybody on that one?
Hey, Roger,
Yeah.
I wanted to make like just a high level comment, which forgive me if I'm just like super stating the obvious, but like it took me a little while to just boil down this concept into like just a handful of words. Okay. So like
Okay.
in many models that we're used to, we'll predict something like a class or whatever, and we'll have probabilities. Technically, you know, we're outputting logits before the softmax, right? But more or less, we have a neural network and it's directly outputting probabilities. Okay. And at the end of the day, what's different about a diffusion process, like don't get caught up by the fact that it's this multi-step process of diffusion. At the end of the day, all it means is that instead of directly outputting logits, which says this is the probability of A, this is the probability of B, we are directly outputting what we think the score function looks like, the gradient of the log probability distribution. Okay. How you use that particular prediction, the gradient of the probability distribution, is you do this iterative process in order to actually generate an actual prediction. But if you sort of set that aside, like fundamentally what's different is instead of directly predicting a prediction, we're predicting the score function. Oh, sorry, instead of directly predicting the probabilities, we're doing the score function on the probabilities. And that, I feel like, takes a little bit of the mysteriousness out of it.
Right. So that's it. That comments the diffusion model in general, right? Not in this specific application, but
any
any
diffusion model.
Right.
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 So when you have a diffusion model, there's this extra machinery you need because let's say I've got this really, really accurate score function. Well, how do I actually use that? Okay, well, there's this multi-step process where you start with some noise and you eventually wind up with a prediction. But that aside, training a neural network, like this is really just very much using gradient descent to train a neural network, just like we've done before. It's just that right now we're not predicting like Y's, we're predicting score function values.
Right. Which is,
I don't know if that's helpful for people. It kind of helped me to just sort of, you know.
Yeah, and the one thing, Ted, that came up when I was reading through this that they made a point about was there was another model that they compared against, this implicit policy, which is an energy-based model. They kind of characterize this as this is a probability estimate. Whereas in the diffusion policy, we're predicting let's see, it's the gradient of the log probability, right? And the difference they said is that the diffusion policy, as opposed to the implicit policy, seems to is more stable to train. And I think they said it's partly because you don't have to estimate the denominator that you get in the when you're trying to predict the probability.
Yeah, and I don't know if this intuition's right, but the way I think of it, if you look at the diagram on the right, I mean, it's a little hard for me to see at your resolution. You don't have to do anything, Roger. But essentially, those blue things are like arrows, okay? And what a well-trained score function will tell you is areas that are flat and areas that are sloped, and if they're sloped, in which direction, okay? And these diagrams are nice conceptual diagrams that are only 2D, but this will work in a very high dimensional space. So like when you're doing images, 64 by 64, 3-color channels, it can be tens of thousands of dimensions and it'll give you a slope in 10,000 dimensions, okay? And apparently, I don't have great intuition, but apparently, like just simply knowing whether it's flat or it's sloped, and you don't have to get the slope perfect, right? Because you're just trying to head towards the high probability areas, right? I mean, ultimately, yes, I don't know how to say it, but like, I think it's more robust because if you're off on the slopes a little bit, that doesn't like really break things. But if you're directly outputting a probability and you're slightly off, you're just slightly off. There's no recovering from that, you know? So, and in this case, it's using an energy formulation in order to sort of, I don't know how the right words to use, to capture, to express the probabilities.
Right.
You know. Anyway, I mean, I've said things that later on I realized were really wrong. And so sometimes that's the process before really understanding things. But I hope that makes some sense. I hope that helps people because, you know, if it says there on the right, gradient field. If you know that gradient field, you can indirectly derive the probability distribution from that. And we don't actually try to numerically calculate that. We use this process where we have noise and we jiggle it a little bit, and then after so many iterations, you know, we have a sample.
Right. Yeah, so this is maybe a little bit more advanced and maybe off topic for right now, but you can derive one for the other. Given the gradient field, you should be able to derive the log probability. And vice versa.
You can, but I think it involves integrating from like negative infinity to positive infinity across all dimensions. And so we're not actually going to do that.
Yeah.
That's where not needing the normalizing constant comes in, because we could do that, but then we would need the normalizing constant.
Right. I guess what I was wondering is if it's more stable to train the diffusion, the gradient field, once you've got a good gradient field, but now inference takes longer because you have to be iterative with the gradient field, right? I guess what I was wondering is, is it possible to then take the gradient field, do the integration to get a model that does probability directly, so that the inference is quicker?
Those are the samplers that they talk about, right? Different samplers which are faster over time, and once you have the modeling based on the SDE or the ODE mapping, if you may, right? Then they are able to apply those differential equations optimizations that exist for last century or more, right? Which have been applied in mechanical and civil engineering and whatnot, other worlds, right? So they leverage those same optimizations that they have there to denoise or sample, if you may, in this case, faster. So you'll see some diffusion model samplers which can do it in 4 steps. So instead of thousands that we had in the original paper in 2015, it has already accelerated. I do want to add one point before moving on. So this score-based estimation is prevalent since the score-based work came out from Yang Song's lab. And then back in 2020, Berkeley and OpenAI, I think, together collaborated to the seminal paper now called BEPM. That's what brought the noise, denoising, and score functions together for diffusion. Before that, it was probability density estimations directly, and that's when the stability of the diffusion was both not so great as compared to GANs or what they found eventually, and also much longer inference time because you could not apply many of those optimizations that you could do with the score-based potentially. Sorry, Ted, I interjected when you were going to say something about the first point I made.
Yeah, no, thanks. I appreciate it, Dave. I just want to clarify, though, if my understanding is right, these fast solvers, they are still doing this denoising process. They are not what I thought Roger was asking is, can you just integrate and get like closed form probabilities? And they're not doing that, to my knowledge. We still are using the score function. We're just taking fewer steps in order to try to, so to speak, follow those gradients very quickly instead of in lots and lots and lots teeny tiny steps.
That is correct. I mean, the procedure is still to identify the noise, but instead of going to 1,000 denoising steps, it is less steps. But the reason you could do in less steps is because you apply these different ODE optimizations, so like Euler, I don't even know the name, sorry. So all of those optimizations of different kinds.
But like the the other example they have in the paper where it's like the two Gaussians, one in the upper right, one in the lower left corner of the square, right? Like that's a small enough problem that you actually could integrate over that. It's only 2 dimensions, and you could get approximate probabilities, right? So you could say like whatever, the XY coordinate that's near the upper right corner has a very high probability. It's 0.1. And then, other places it's 0.05. And then there's places where it's really low, 0.0001. And then when you're near that lower left corner, then maybe it, rises up again to like, 0.03, right? I think you could, because it's a relatively small grid and you could get somewhat accurate probabilities, but that's only because this is such a tiny problem, Roger. If I was understanding your question right.
Yeah, I was just trying to understand, is there diffusion is more stable to train, but more of a pain to use. Was there a way to take the results of the trained diffusion model and make it such that you could have a faster inference model out of it?
At the moment, there's no free lunch.
Okay.
There's faster inference, and then generally speaking, the faster your inference is, at some point it starts introducing errors.
Mm-hmm.
So like DDIM is very fast, but I think for lots of applications, it's going to introduce more error than it's worth, the hassle. And then, yeah, there's no way to just sort of integrate over all this and store it. Again, I mean, not for decent sized problems.
Right. Okay, well, let me, unless there's anything more, I will go ahead and jump back then. How's the bandwidth? Are things getting updated more quickly then?
Seems okay-ish now.
Okay.
Slightly better, readable, yeah.
Okay, so I think we've been through the paper already. I don't know that there's anything more in the paper that we needed to cover. We saw the video last time that covered the topic as well. And I'll repost this document, I guess, in agenda in case anybody wants the slides, access to the slides. But so they did both simulated ones and real life ones. These are pictures associated with real life ones. The ones when I was looking at the code, I mostly looked at just their collabs that they provided. It's a little simpler to follow through. But I think the policy is supposedly the same for the 3D real life tasks as well. I think we were down in here someplace. So yeah, I think we pretty much covered last time. So what we can do is I played around with the data a little bit. They have, again, so one of the core concepts of this is that it's using demonstrations, a somewhat limited number of demonstrations to train this diffusion model to achieve that task. And the goal of the task is kind of in the diffusion model, built into the diffusion model. So the ones that I was looking at because I was doing this push T example, they have a script that basically it's a 2D simulation, and they have a way for users to use the mouse to provide the human demonstrations. In the case of the robot, real robot, I think that's where they had, oh, in the video we saw an example, but they had some sort of mouse capture device, so the user would sit in front of the robot and use these space mouse capture devices to record the sequence. So both of those are captured and used to record the state of the robot. Some of the other ones, and I didn't look into these, but some of the other ones come from some of the other simulation benchmarks. The RoboMimic was one, and the Franca Kitchen was another. So there are other ones where they've recorded episodes of some task, and they were using those as well as their own here. They did both, at least in the case of the push T, they did both state ones where the state data is just captures the position of the T and the end effector, and stored those in ZARR. I hadn't heard of this before, but it's a data file storage API, Python data file storage, or object store probably is closer description. And then the video data, they have the global camera, which looks down at the overall workspace, as well as one that's on the wrist, which I guess they found is helps with tasks that require fine positioning. So the observation for this push T model is basically the position. They called it the agent, so that's the end effector. The block is the thing we're trying to move, and the block angle. So it's basically 5-dimensional space. And in this example, they did hard code the goal. So the goal is not something that's the diffusion policy is conditioned on. It's built into the weights. So one of the things I wanted to do, and I didn't get to though, but is check to see if that would be something that is, if you put that in the conditioning, would that allow you to set the goal and then have move it to that position? I think, Dave, I think you might have pointed out that in the pizza, when you're spreading the pizza sauce, he was moving the plate around, and I saw someplace some examples of the training data for that, and they did locate the tray in different locations each time. So it was conditioning, I guess, that on the observation. When it saw that the video would show where the plate was.
Right. I just want to let you know that on my end, the code that you are displaying is not really visible. It's like maybe it is just now about getting more clear, but hardly more clear is what I would say.
Oh, wow. Okay, then this is probably going to be very difficult then, because I'm going to guess that when I pull
Hey,
this,
Roger,
yeah,
when you did share, did you say share video when you did the share button?
I did. I'll
Can you try undoing that and see what happens?
Yep.
Because your video, your face is fine, so I don't think it's a bandwidth issue.
Okay. Oops, I did. Hold on, that was the whole screen. Let me.
It's definitely
Just-
better, whatever you did.
Yeah, I just want to be clear. When I said your face is fine, I didn't mean like,
Right.
I don't want this to get more awkward than it already is on a regular basis.
Okay, how about that one? That's
Infinitely better.
Yeah, awesome.
okay. I don't know why that
Even
okay.
using a non-diffusion model, you can actually identify what the letters are now.
Okay, great. Good.
We were
Okay.
applying all the denoising to read what
And it
you
wasn't
read.
working. Okay, so yeah, so that's kind of what the data looks like. And there's also, they have a whole, you can download the data sets. They have a whole bunch of these. I forget how many, it's 200 or so, I think. So this is one of the cameras from real life. The robot is being operated by a space mouse. So they're using that to position the T. I think they also provide robot pose data at the same time, but in addition, they have the video for training. I started looking at, we'll probably want to
Hey,
rerun
Roger,
that.
in the previous slide,
Yeah.
was the second right one the wrist camera, and the left side
Oh,
is
this
the
one down
yeah.
here? Yeah. Yeah, right. So this should be, they might not be exactly synced, so you might be seeing, they're pretty close. Yeah, but one is the overview camera, and then the other is a camera right on the wrist. And the way they described it is that, the overview is where most of the work gets done, but when you need to do fine positioning, that the wrist camera helps. So you can see it's easier to see how close the T is in this example.
Right. Sounds good. Thanks.
Okay. So I played around with, we'll look at the code as well, but this was, I ran through, and it turns out one thing I discovered is they have about 200 episodes that they call it, where it's been manually moved. And then when they create their data loader, they take those 200 episodes and they break them up into little pieces. So there'll be a fragment with 2 observations, and then the next 16 actions that should be predicted by those 2 observations. So there's, I don't know, 24,000 separate training observations in the when you're running through the data loader, when you're doing the training, but it's only built out of a couple hundred of these. And here I did 2 different ways. This is what I'd been doing. I found another way to do it. I'll show you in a second. But here I'm recording. The blue is the center of mass of the block you're trying to move, and the red is essentially, the gray is where it's told to go, and then the red is where it actually went. So you can see these motions that you get out of here. They're pretty, I don't know what I'd say. They're just, they kind of seem messy. I'm almost surprised that it can learn from these. But that's the
So
type
where
of,
is the gray one here? Sorry, is there a gray one you said?
yeah, there's a little gray. It follows, it's right underneath the red one. It's just plotting what the action was. And remember, action, in this case, they're doing position as an action, position control. So the action is, where do I want the end effector? And the red is, when I observed it, where is the end effector?
And the
Go ahead.
center of mass is for each of those bars of T, like the top and the straight, the eye, or is it just center of mass of one of T?
It is the center of mass of T. So this is, this would have started out here. This guy came around and pushed it, and the center of mass, as he pushed it, shifted down to this location, the goal location.
So what is missing in this one is the orientation of
Orientation,
T.
right. Now, I trying to use Matplotlib, I wasn't able to, I was struggling a little bit with that. Let's see if we can find, down here, I plotted the data. Here's the training episodes. Let's see if this worked. So this is the actual training plotted in the environment. I realized you could do, and it looks more reasonable from here. I think I did like 20 episodes or something. Does that make sense?
Right, right. But in those plots, we didn't have the orientation. Now it says 206 episodes here.
Yeah, there's 206 separate training episodes and broken into 24,000 examples in the observations, right, to be trained on. Because you just basically you can grab any portion of this, right, and train on what do I do next if I'm in this situation. It makes more sense here because you can see the shape of the two objects.
Right, right.
But if you look back here, this is the actual data that you're getting plus rotation.
And does it? I know
Okay.
it talked about the 6 degrees of freedom, which is does it include the? There is constant pressure with, like, it's not like speed up in this direction. It's just constant steps, constant pressure.
Right. So in this example, when they did the physical one, let's see, you can see some of them here. When they did the physical, it is a, is it 6 degree of freedom? Probably. It's got, I don't know how many axes on it, but they're essentially constraining it to 2 degrees of freedom, just the coordinates on the surface of the sheet. This is like the baseline, hello world example. They did several others where they did more degrees of freedom. This robot here, they are turning the cup right side up, or excuse me, upside down, and that was done with in a 6 degree of freedom end effector. That make sense? Does that answer the question?
It does. It does. I mean, it's a hypothetical one where, in real life, you have some other factors. Of course, more degrees of freedom, but also how much torque or force to apply, right?
Right. And I think that I'm pretty sure it applies to all of them. They said that they didn't use, they did not control like the arms, like the individual angles. They were just dealing with the position of the end effector. And that's what they were controlling. And then they used, some sort of function to translate. If I want the end effector to be here in this orientation, where does my robot have to be?
Got it, yeah. So I'm assuming in that pizza sauce, they have like the flow of pizza sauce is controlled by some other factor, and they do not control how much to turn the ladle, if you may.
No, actually, no, they do control that. There isn't a flow. They scoop it up and then pour it on the onto the pizza.
So there are multiple degrees of freedoms, and
but what I'm saying is I don't think that their control algorithm controls the angles of the joints directly. The diffusion process controls the position, the 6 degree of freedom position of the end effector, but not the robot joints. And then they use some sort of solver that says, if I want the end effector at this position, this pose, what angle joints do I need to get that? Does that make sense?
Yeah, basically they're just doing a function call, and that's a solved problem.
Yeah. Okay, so that was what I was thinking for data, to look into data. I don't know if there are any other questions on that. The next then was looking at the code, and like I said, mostly I just looked at the code that was in these notebooks. So they provide 2 notebooks. One is a state-based one, and one is a vision-based one. They're both this push T task. I was unable to get their whatever this configuration, this setup, install pip packs and packages and all that. That didn't work for me. So if you are looking to make it to work, I've got the changes to run in a current Colab environment right there. The import, so the only thing I'll show here is, so they built this on this 2D thing on Pygame, which basically is a Python interactive game framework. They use that for events, mouse events and stuff like that, display. PyMonk is a 2D physics package, and they use that for modeling the collisions and friction and stuff like that. Shapely was another package they used basically just to look at the overlap between the goal position and the actual block position at the end. The environment. So I think we've played with this before, and when we were looking at reinforcement learning, some of the AI gym stuff. That has, first of all, it's been, I guess, upgraded. It's now called Gymnasium. And that, I might have mentioned last time that some of the examples in there used to be using Mujoko, if I'm saying that right. Mujoko was purchased and made open source by DeepMind, and so that's now available to play with. It is a fairly involved, fairly advanced 3D physics modeling environment that's been used a lot in our reinforcement learning. It seems like it's the one that they're using for a lot of the robotics playgrounds now. Okay, but for this one, we're just going to stick with this Pygame and Gymnasium, AI Gymnasium model. The gym, I don't recall if I got a snapshot from that or not. The Gymnasium, basically, it makes it easy to create an environment that you can interact with and observe. The key thing is that you select the environment, and then there's not very many calls. You do a reset, which will return an observation and some additional information. And then you can sample from an action space. This is just a random sample. Your policy would select your action. Then you do a step on the environment with that action, and you get back. So this is extended. It used to be just observation and reward. Now you're getting observation, reward, a status if you're done. I'm not sure the truncated info. Info I know is a dictionary of just additional information. Truncated might be that you run out of time or something like that. It used to be just terminated. And you just iterate on this, and that's how you use the OpenAI, what used to be OpenAI Gymnasium. I think this is now moved out of OpenAI and is more of an open source model. Yeah, it's a maintained fork of it. And it sounds like it is the one that's getting the maintenance now. So in this code, we're following the same, we'll follow the same things. Some of this stuff is just translating stuff, so you can draw the screens, those little the T and goal and all that, and integrating. There's something about the PyMonk and Pygame using flip-flopped coordinates, so you have to translate between that. This is converting the PyMonk to Shapely, just so you can use an overlap computation. But here's the environment, the push T environment. Initialize, obviously you need to initialize. They have an observation space that is 5-dimensional. This is generally small stuff. I didn't look at this actually for the vision-based system. That might have been interesting because the model would have had a bigger observation space for sure, because it would have had images. Action space is pretty small here. It's just the 2 coordinates of the end effector or agent, as they call it. Reset moves everything back to its starting location, and then here's the step where all the work happens. In here, this space, I believe, is the screen keeping up, by the way, as I scroll back and forth?
Yeah, it's good.
Okay. The space, if I recall, go back up to the init section. There's not space, is nothing there. I thought that that was a, no, maybe I missed it. This is the physics model step, because the physics model, PyMonk, also has a kind of a reset and step. And I think this should be the space, should be the physics model. I'm not sure why I'm not seeing the initialization of it. Anybody see that? Am I missing something here? Okay. Anyhow, let's just take it for granted that this is
it might be
updating the
buried in like that set state, whatever.
Is it down below?
I noticed like in reset there was like a set state or whatever.
Oh, okay.
So the space might be getting
Oh, I see what you're saying.
inside
Yeah,
there.
down there. Yeah. It could be. Set state. Yep. It's, or at least it's expecting it to be initialized by now. So somewhere, anyhow, it'll initialize that space to be the physics model. So what it does is whatever this action horizon that they call it, it'll execute it that many times. So it'll update, it'll hang on to it for that many times. That's where the simulation is running different than the control model. And the computer reward, basically looking for, does it overlap? What's the IOU of the block and the goal area? And computer reward based on the coverage relative to some threshold. So if the coverage gets above their threshold, then it's this run is done. Okay. Any questions on that part? Pretty straightforward.
Yeah, I mean, it seems to make sense. I'm interested less in how did they do the T simulation. I still have some questions about the algorithm. So like, I'm interested to see if we can see that code. I don't know if you're working your way towards that, Roger.
Well, what we can do is kind of run down to the run down where they do the training is probably the network. Basically here, they're just doing a UNet that's one-dimensional UNet or conditional UNet, position embedding using sinusoidal and position embedding, and then they kind of build up the UNet here. I'm not quite sure why, maybe because they had to insert their conditioning in it, because they do use what is it? The diffuser's library that's from Hugging Face, and so I think they would have had access to or to UNet models, but it was probably the way they integrated their conditioning that they wanted to build it. So they have, you can see where they're building up the residual net part here, condition U1 network where they do the downsampling and the smaller networks, and there's a mid-level network, and then a final comb on the output.
So Roger, did you say it was a one-dimensional UNet?
Yeah. Yeah.
Why is it only one-dimensional? I thought the action was two-dimensional, an X and a Y coordinate.
But they're flattening it. They flatten it when they send it to it. I don't know if there'd be an advantage to do it otherwise, but that's what they did.
Oh, sorry. It's not length one, but it's one dimensional.
Yeah, yeah,
Okay. Okay. Fine. Never mind. Sorry. I'm being
yeah.
dense.
This might be the section, Ted, that you're asking about. Then how do they do the training? So this is one you can run in. I haven't actually run the training in this one. I've just been cheating going to the weights, but supposedly you can run it here, collab in about an hour. They have, so they use the exponential moving average. That is, they said that that's the one that they use for prediction and inference on the end. I'm not sure if it's not like the other models, I don't think, where you have them. Sometimes we've seen them where you're using an exponentially moving average in combination with the kind of student. I don't think that's what this is.
I think this is just when you're training, it's
it kind of goes up and
smoothing,
down, right?
it's
Yeah.
smoothing the weights,
Yeah.
your neural network weights over whatever steps, epochs. So
Yeah.
that's not relevant to the algorithm. You can use exponential moving average smoothing with any neural network.
Right. It just makes the checkpoints more stable.
Mm-hmm.
So all standard stuff here: atom optimizer, cosine learning rate, standard stuff. TQDM, that's just a package for the progress bar. And then they're going through this is, I believe, where they are actually, I've not seen this before, but this progress bar appears to use the data loader object. And it is returning, I believe,
Yeah, data loader has a length that it'll return, even though it's never
right.
loading them all in memory.
Right.
So that's your epoch, which is, I think you said it was what, 20,000 something?
Right, 24,000, yeah. So in the end, we get here where we have the batch coming out of this TQDM, and they extract. It looks like it's in a structured dictionary or something. So they extract the normalized observation, the normalized actions. They took both of those and normalized the data. It was 0 to 512 was the observation. They brought it down to where it's in a -1 to +1 range. Same with the actions. B is the mini batch size, so it's the number of entries, number of observations. And then they're setting the conditioning. This is on that observation horizon. How many of those observations do you use for conditioning? And here's where they did the flattening, or one of the places they did the flattening, I guess. The condition was also flattened. They sample some noise, and then this structure here, this noise schedule, so this comes out of the diffusers. It's a noise scheduler, and they use it to add the noise. So this would be the normalized action. This would be the noise profile that you selected, and it looks like we've selected a different one for each entry in this mini batch. And likewise, they sampled time steps. So between 0 and the number of time steps they have in the diffusion process, they sample a different one. So each entry will have a different noise and a different time set. So that's the diffusion time step. The result is the noisy action. So that's added in the right amount of noise. They are using, so this is that UNet 1D conditional UNet that we defined earlier. They're using that to predict the noise given the noisy actions, the time steps, again, meaning how far into the diffusion, how much noise has been added, and in all cases conditioned on this observation that in our case, two state vectors that we've captured earlier. Just an MSE loss between the predicted and actual noise. Standard stuff for loss, propagate, backwards propagation, optimizer steps, learning rate steps, and the moving average step. And that's it. Pretty much standard standard diffusion training.
This is cool. Thanks, Roger. So when I'm reading this, if I'm reading the code right, for each observation, there's sort of this like history or whatever. That's like the film thing. But we're only making one action. There's only one action prediction up above that. The number of actions equals n batch or whatever.
Right. So that is a vector, though. It's a vector of actions. So it's a sequence of actions.
Is it? That's the thing that I was trying to figure out is,
okay,
are
well,
we
let's go.
running the model 6 times if we want to predict the next 6 actions, or are we running it once and it's spewing out 6 actions all at once?
We should be able to find out here, shouldn't we? Let's actually, it's going to be where this model is instantiated, I think.
Yeah, and you might be able to see it where it gets actually takes the prediction and then runs steps, because is it doing prediction step in the gym, or is it doing prediction, oh, look, the prediction is X many steps long, so we'll do step.
So this is a noised action. So that's the batch entry. It's the prediction horizon is how many steps we're going to predict, and the action dim would be
2 in this case, right?
In
X
our
and
case,
Y.
2. Yeah. So that this is the network. This is the UNet 1D. You're passing in the noise action of that shape. Again, this is the iteration. Which step in diffusion are you in? And then a flattened conditioning observation. Does that answer? Does that convince you? Is it right?
I'm not sure if I'm completely clear on this.
So
I guess maybe there's code in the data loader that that we haven't looked at that would grab like 4 or 6 or however many actions
yeah,
that we're not seeing.
Also, well, actually, this entry is saying different. I would have expected to see the prediction horizon to be part of the model.
Right. If you're doing it in one pass, then you have to have the 2, which is X and Y, times however many your horizon is at once. So if you wanted to do 6 predictions, you should have 12 numbers in your vector.
Yeah, let's see here. See if I can, where's the output here?
Yeah, I don't think you're going to see it because I think the unit will accept any size.
Okay. Dimension. Oh, okay. Well then, so the UNet accepts it. How else do we answer your question?
So when you actually run the simulation, what you should see is it's going to call the model to make a prediction.
Yeah.
And it's either going to call the model and get back, like, let's say 6 predictions and then run steps 6 times in a for loop, or else it's going to call the model 6 times and get 6 steps. Does that make sense?
Yeah.
So there either is a for loop around make prediction or there isn't.
Yeah, there isn't. You do get the 16 steps out. I'm just trying to, on the spot here, I'm not sure if I can, I think
not sure if you can find that code.
It's not even connected. Well, what you want to see is what's the dimension of what's coming out, right?
No, really, I just need to see if there's a loop or not.
Loop on what?
Make prediction.
Oh, okay. Well, we can look at inference right here. This is the same thing. So when you're doing inference, you got your environment, instantiate the environment, your progress bar. We're just doing a batch of 1 in this case.
Okay.
This is managing the 2 observations to be a single one. You normalize them. This is flattening your conditioning observation. And here your action, B is 1, batch size, prediction horizon, and action dimension. So this is 5 and this is 16. And then you iterate through here. This is where the noise scheduler manages the updates. Each time you're calling it with your noisy action, right? Coming up with the prediction, passing the prediction and the noisy action down to this step, which adds the right amount.
Yep.
And then you get your actions out. So the model predicts 16 actions each 5, or excuse me, in this case 2, sorry. The observation is 5, the action is 2. So 16 times 2. And it makes sense. It makes sense because that is, I can think of the noise prediction model as being able to kind of draw correlations between the steps, right? It should be the smooth action sequence.
Okay, yeah. So we only made 1 prediction, but then if you go about 8 lines down, you can see for I in range length of action.
Yep.
So,
yep.
So, and that's based on your there was 2. You do more predictions than you actually use, but whatever the part that you're going to use, then you loop over that and you actually take steps there. You can see right after that equals environment step.
Right. There's the action horizon is how many of them you're going to use. Prediction was horizon, how many you're going to predict, and action horizons, how many you can use. And then you just run the environment through however many you're going to use, sending it the action, you get the observation, you get rewards, you accumulate, they're storing away the image, rendering it, update progress bar, and that's kind of it.
Okay. So I don't know, I may have been the only one that had this difficulty, but like if we go back to the paper, there's that diagram, and I felt the diagram was a little bit loose where it's just showing like multiple actions and it's showing, you know, that main diagram that shows how the thing works.
You're talking about this one?
Yeah. So that middle section, A, general formulation, right?
Yeah.
So it really is stacking multiple observations of history and packing them in there, and it's stacked, and then it's making multiple action predictions all in one fell swoop in one inference call, one prediction call.
Right. So the little a's are the individual actions, and the capital A is the action sequence, it looks like.
Right. So it's outputting one entire sequence each time you run inference just once.
Yeah.
Yeah. And so that's what basically what you were saying is that, hey, it can be smarter. And the thing they talked about was some other model could be prone to say, well, I could go either left or right. And if I predict one action at a time, I might accidentally go left, right, and just like jitter back and forth and not make any progress.
Right.
Whereas I assume if you predict 4, 6 actions in a row, you're never going to do that.
Right.
And then by the time you've taken whatever, 6 action steps to the left, now you're no longer near the halfway point, so you're probably far less likely to start going back to the right because now it's shorter to keep going left.
Yeah. Yep.
Hey, Roger, I may have missed it, some internet issues here, but the diffusion policy that goes up to the right box, right? Either observation, okay, CNN based or the transformer based.
Yep.
Did we see that code as well?
What we saw was
We just saw the noise prediction, right?
We just saw this version. The CNN based is the one they've implemented in the notebook.
Well, actually,
So
this one, it's not even CNN because this one is using a simulation. So you have exact X, Y coordinates for the center of mass, don't you?
Yeah, but this is the model. This is the CNN based epsilon theta. And that was the 1D UNet that we saw.
Oh.
Right. So
Right.
we saw the linear observation.
With the conditioning, they added the conditioning. Yeah, we can probably find, if you want, to go back to the model.
Yeah, we have time, so if you can.
Yeah, we should be able to find, this is where they're building it. They're putting they show a residual network. Did they, in the paper?
Yeah, they saw that.
They didn't really show residuals here on this paper, but they show residual connections in here, it looks like. They have down conversion blocks, so they'll do a couple conditional resid blocks. Let's see where they define that here too. This is the conditional residual block. It's mostly a conv 1D that they take out of PyTorch, but they take the first conv 1D and compute an output. They take the condition and embed it. They take the 2 dimensions of that embedding, and they use that to take the output, scale the output, and add a bias to it, which came from the conditioning, right? And then run that out through one more conv. And then this self-residual looks like another conv 1D. So they actually have like 1, 2.
No, self-residual is just what is it called?
Oh, that's
before
the functional
normalization.
interface?
Yeah, X
Okay.
plus
So it's not separate. Okay.
Yeah.
And so that kind of matches up with this, right? They're taking the action, they're taking the observation, embedding it into this A and B, using the A and B to modulate the X, and then run it through another conv 1D.
So A and B are your bias, and A is the scale, and B is
Scale
the
and
bias.
bias.
That's right. Yes.
Yeah.
That's
Scale and
cool.
bias there.
And so then it basically learns the weights to calculate A's and B's.
Right, to modulate it.
Biases.
Right. Yep.
And then in the case of push T, do we have any actual conditioning data? Is that the goal? Is that the conditioning data?
Yeah, in push T, the observations are, we have 2 observations of the 5 state vectors, which is 2 dimensions of current agent, in other words, the robot arm, and 2 coordinates of the T center of mass, and 1 coordinate of the T rotation. Does that make sense? That's
the observation. I'm talking about the conditioning.
The conditioning is, the observation is the conditioning. See, the observation here becomes the conditioning that goes into here, observation OT. So you observe, in our case, state, right? 2 of them. It could be more, but in our case, it's two states. You're using that, transforming that through. That'll tell you kind of where you're at. It also, you get some velocity information in there because there's two of the states that we get. that information then is used to modulate your actions. Does that make sense?
Yeah, so the action just starts out as noise.
Right. Yep. And that's if you look at this picture, they're trying to capture that. These are all, this is the action vector initially, is just noise. And then gradually the noise is reduced as you iterate k times through the diffusion. The noise is reduced until all of the little actions line up. Does that make sense? And the cool thing is, right, they're going to line up in a way that's smooth. They're going to line up in a way that matches those 200 episodes of training data. And it learns that, you know, from all that, it learns to, where do we got it? This is what it learned from the training data. It learned to do that move based on the position of the end effector blue and the T block. It's kind of cool.
If we go back to the picture in the paper,
Yeah.
right? So in the CNN base, which is what they have, you have observations OT, you have actions A at the bottom, and then there's a K times denoising. Is that right? But cross K over there is the
This
steps.
K? This K you mean, or?
Yeah, this K.
Right. So the
Right.
K, I guess is it also modulating? It might not have modulated. It might have been concatenated. That's the time step that's put in. It concatenates it with, it embeds the time step K and concatenates that with the global conditioning.
It's funny, I would have called the time step T, but okay.
Yeah, I mean, it's time step only in the sense of diffusion. This is in a real world where we actually have time steps of robots moving and environments stepping and stuff. But they confuse a little bit here because these T's up here, these little T's up here, those would be the clock.
Yeah, actually, I just realized something. What had me confused about this figure 3 is that they've mixed the architecture diagram with the data flow when you're running inference. Because in an architecture diagram, I don't really give a hoot that you do K diffusion noise steps, right? And I don't care what your schedule is. I just care about my architecture diagram.
Right, but if you're describing the diffusion, this epsilon theta, it will always accept the diffusion step, right?
No, but what I'm saying is that, for me at least, what's confusing about this diagram is that it has both visually stuff that shows like multiple layers of the architecture, but it also has stuff that shows in time things happening K times.
Yeah, right.
Now, I can understand that you're like space limited in a paper and you might not want 2 separate diagrams or whatever, but it just took me a little while to figure out that's why this is confusing, because if it were purely an architecture diagram, it would have been really clear that big A is my input and it's 4, 6, however many actions, et cetera, et cetera, et cetera, right?
Yeah.
Because there's no time in it. It's just, hey, I'm showing the shape of my inputs and the shape of my outputs.
Yeah.
But here they've really confused it because now they're talking about, oh, and we're kind of like moving from left to right in time and we're doing K iterations of it, which, like, you know.
Yeah, it's kind of like these arrows here are time. This arrow is a zoom. Zoom in on the diffusion policy.
Yeah. And so then the arrows with the convolutions, that's not time, that's architecture model data layer flow.
Right. Yeah.
So yeah, and then to make things even more confusing, the robots are operating in real world time.
Right.
So you have real world time and you have diffusion step K time, and then you have data flow layer stuff.
Yeah. Does it all make sense now, though?
I think I finally caught up. I don't know about everybody else.
That's good. And the reason I brought you to this picture was for this
Oh.
delta E on the top of that picture.
Which one?
On the observation box, the B and C diagrams of the film, the feature-wise linear modulation.
Oh, these
On
two?
on the very top, it has delta E action.
Yeah, actually, it's
So
gradient E. It's nabla E.
nabla E, that's right. Yeah, not delta. My bad. Yes. So it is the
The gradient of the expected value of the action sequence.
so is it the score?
Well, see, this is where I don't. We saw the code. The network that epsilon theta learns to predict the noise
No, exactly. Yes.
that it thinks was added. I don't know what you call that. Is that a score? It equates to, or it's similar to the gradient of the log probability.
Then if it is score, then it is the gradient of log probability, but the diffusion step is supposed to estimate the noise. And it did say noise over there, noise prediction in the code.
Yeah, it predicts the noise, but I don't quite know if that's the same as a score function.
Yeah.
I was kind of hoping you'd answer that one.
I'll have to go back and look at the code, but yeah, maybe I can look at it offline and we could discuss it on Slack.
I mean, the magic all seems to happen down in that this guy. This is where it's looping for diffusion. It's predicted the noise here at this time step. This will then, okay, we started out with completely Gaussian noise. It's predicted what it thinks is the noise there. It sends it down to this noise scheduler, which is the diff users from Hugging Face. It's their little package for diffusion. It uses the time step information, the predicted noise, and the current estimate of the, in this case, the action vector.
So Dave, I think technically speaking, the noise is really an integral over the score function. So let's just use a uniform time schedule for simplicity, okay? None of this like trying to do the fewest steps possible, but let's just assume it's 1,000 equal steps of Gaussian noise, right? We're predicting the difference between step, say, 499 and step 500.
Mm-hmm.
So, you use the gradient, but what you're really doing is you're predicting the integral of that gradient from T499 to T500. And that becomes more important when you're doing unequal size steps, because now if you do a much bigger step, then even for the same size gradient, you're going to get a bigger number because you're doing it over a longer window.
Yeah, but yeah, so in this case, it has a set time steps, right? For K noise scheduler dot time steps, whatever that is set to. It's iterating during inference time. It has to go through all of those steps.
No, because that's why you call the noise scheduler function, because you give it a T and it tells you how much noise is, or K, and it tells you how much noise is associated with that, and it does not need to be uniform. If it was uniform, then you could just say, okay, fine, total number of steps is 50. Let me just divide the Gaussian noise by 50, the step number by 50, and that tells me how much noise. You have to call noise scheduler because it's an uneven schedule.
So this one we might need to go offline to look that up. I'm not, my assumption, Ted, was that the noise, essentially, noise prediction is predicting the gradient, is the same as predicting the gradient of the log probability.
You're definitely using the gradient either way. I just think it's not technically exactly the gradient. It's a calculation based on the gradient. So at a minimum, it's sort of like the gradient times how big of a step you took. Because if you take a teeny tiny step, you're going to get a small number. If you take a step that's 10 times bigger with the exact same gradient, you're going to go 10 times as far.
So the direction is right, but the magnitude is different. Is that what you're saying?
Depending on the size step you take, yes.
Okay.
And then
okay.
I believe the ODE solvers and add additional nonlinear dynamics so that it's not really just times 10. It's a little bit more precise than that.
Dave, is that something you could look up, or maybe we could look up together before the next session, because you're pushing my boundary here on diffusion process.
Yeah, definitely. Definitely we'll look at it.
Okay.
Sounds good.
Okay.
I will work with you on that.
And I will, and maybe I'll save this last thing until we clarify that, because so what I tried to do is I went through and essentially ran a grid of actions, fed it through the prediction, and looked at the output. And I did it. So this is the prediction. And there's different variables in terms of where the block is, because it's conditioned on where the block is and where the end effector is. And I thought I could see this. This is supposedly a prediction, or a representation of the noise prediction, or the score function, if I'm using those terms correct.
Yeah, so basically it's whatever that XY coordinate is, that like the X coordinates around -0.5 and the Y coordinates around 0.25. You can see that's pretty much sort of like the global maximum of the probabilities, because the gradients are all pointing towards the top of that hill.
Exactly. Yeah. So after, I think I did 16 moves here. So the 15th action predicted from in that configuration would be out in here, and it moves when the block moves. So it's trying to get to the block to make contact.
That's cool.
And the same thing here, I think in this case, I was looking at a point that is only 2 steps ahead. You can see that it's going to be moving to a place that's close to its current location. And then this one, I varied how far forward it is. So you start at prediction, the next action is going to be close, and you can see that the actions follow getting closer to the target. If you can see the kind of the high point moves.
Mm-hmm.
And then this one is really interesting. I don't understand here, but this is varying the timestamp and how the score function changes. Uh-oh, why is that one not working? Oh, darn, that was the fun one.
It's stuck at the end. Can you manually take it back to the beginning?
You don't have the loop selected at the bottom.
Oh, that's what it is, yeah. Yeah.
Now you
So-
reflect. I don't know if you want to reflect on me. Oh, that's fine. Yeah.
So this is really, I don't know what's going on here, but it's like early on. So this would be, I'm pretty sure I do step minus 99 minus. Oh no, this is, so what? Yeah.
Yeah,
this is
that
step.
radio select below the buttons, can you change it from reflect to loop? That way it'll only go forwards. No, yeah, there you go.
Yeah, so it's actually out here is when it's out on this end, it's step 99.
Hmm.
And early on, you can see it gets,
So early on, it looks like it's bimodal. It could either go to the right a little or it could go up.
yeah. Yeah, I saw that too, right in there,
And then
right?
eventually it commits.
Yeah. Really interesting. Yeah, you can see that bimodal, can't you? Like I could, whatever I need to do, I could go to either side to do this.
Yeah, and so then what happens is as you go later and on through the diffusion steps, you're supposed to be taking smaller and smaller sort of noise, you know. So by that point, you should have committed to one of those modes, and that's why you see that the answer has to be unimodal.
Mhm.
That at that point, it should only be making small perturbations. It shouldn't be giving
Interesting.
you big choices.
That's interesting, yeah. So the decision in these bimodal things, the decision is made fairly early on when the noise is high.
Right. So to use like a image generation analogy, okay, early on, it could decide whether the person is facing left, facing right, or directly facing the camera.
Yeah,
And so you could say it's maybe like trimodal, right? But once it's committed to that decision, then the eyes and the nose better be in the right places relative to where you are if you're facing left.
yeah.
You no longer have those other options, right? Early time steps, you have those. Later on, again, I'm saying if you were doing a diffusion of a face, you know, a headshot, right?
Yeah.
So I think this is a similar thing, right? You can push the T from the right, or you can push it from the top, or whatever, you know. But later on, you're just doing fine adjustments. You're not making big decisions.
Yeah. So I'm not sure what it is we're looking for. This is the output of that noise prediction network. I like I said, I'm not sure, is that this equivalent of the score function, the gradient of the log probability? I think it is, but and this fits if that's the case. But anyhow, it was very interesting to see that.
So my interpretation is that if you start with a noisy image and you follow the gradient for a little bit, you'll get to the image at the next time step. Then the difference between those two is the epsilon. So that's what these models are actually outputting, is the difference between the two consecutive images.
I thought they didn't do the difference between consecutive images, but they predicted the noise to the original.
Yeah, they just predict the noise at the original.
But the noise
I know
is the difference, right?
the noise is difference between the actual prediction
Oh, sorry.
and
Yeah. I said the difference between the two adjacent time steps, didn't I?
Yeah.
Okay, yeah, no. It's the difference between
These are-
the starting point and the zero noise image.
Yep.
Right. Sorry.
Anyhow, we're kind of running over here, so
Yeah.
I'm going to go ahead and stop recording, and then we can talk about what to do next time.
Those are cool. Roger, did you have to like figure out how to